different materials and different. So now I'm a theorist, so I will give you more like theoretical background, and so I think the lecture, the title of the lecture is Basic Tools for Nuclear Structure Theory. What I mean by that is I would like to introduce the things, the theoretical concepts and the theoretical techniques that you need for the next 3 weeks of this course. Okay, so it's not, of course, I'm not going to discuss all of the nuclear physics and the nuclear structure tools, but just to focus on those things which I think are most relevant for you in order to understand what the next lectures will explain to you. And so this is a sort of an overview of today's lecture that I will give. And so I will start out with a short review of the independent particle shell model. This was already discussed by Rick, but I will do it again. I introduce a little bit of notation, which is specific to what I say here. And but basically, this is what Rick already discussed. What I will focus on is angular momentum techniques, and so I will explain about coupling of angular momentum, because this is something which you frequently meet in all the lectures that you will have. Right? And I will spend a long time on the problem of symmetry if you have a bosonic system and antisymmetry if you have a fermionic system. And actually, if you put those two together, you will get the concept of coefficient of fractional parameters. And this is something I would like. So I will spend quite a bit of time on this by way of an example. So this is actually a difficult concept. This is something, it's not easy to understand. It took me a long time to get familiar with it. And so this is probably the most difficult thing that I will discuss in the course of these lectures. Now, to give you an idea of what will follow, so this I will discuss tomorrow. So this is my second lecture. I will give a short introduction to second quantization. This was, okay, Rick was already discussing creation and annihilation operators, but I will repeat it and how does it connect to what the usual formulation in terms of wave functions. And then I will spend some time on what I call an algebraic formulation of the many-body problem. What we're doing here is many-body physics. Okay, so we have a system of A nucleons in interaction, and so we're trying to solve that problem. In this course, what is especially relevant is the stationary problem associated with it. Okay? And so what I will show is that there are algebraic techniques which are based on group theory, which you can use in order to solve such a many-body problem. This is actually valid for bosonic systems and for fermionic systems. So these techniques can be used for those systems. And so these are related to concepts. You're all familiar, I guess, with the concept of symmetry and how does it arise in quantum mechanics. There is something which is a bit more subtle, which is known as dynamical symmetry, and this precisely is a concept that is of help in solving algebraically many-body problems. And so these things I will illustrate with 2 examples. So this is for tomorrow. But let me come for today, and let me do a little bit of a review of the independent particle shell model. So we have the following quantum mechanical problem. So we have a Hamiltonian, so the formulation is non-relativistic. So I do a non-relativistic approximation, and I consider the nucleus, or we consider the nucleus as elementary particle. I'm never going to talk about the structure of the nucleus itself. Okay. And so then you have a nucleus. They have each of them have a kinetic energy, and then you have a two-body interaction, okay, which acts on the coordinates of two nucleus. You might have a three-body interaction which acts on the coordinates of three nucleus. And I've used here the notation psi. This is just only clarification I have to give. This psi stands for the position vector, so which is associated with a certain particle k, the position vector of that particle, the spin, which is also a vector, possibly the isospin, and in fact, in principle, you could also here add the momentum associated with the particle, which is this psi is a sort of an ensemble of the variables associated with the particle. Okay. And I do this, well, I will try to do this consistently. Sometimes I just will write only the position vector, but in some cases I will specifically look at the properties of what is the influence of the spin variables of a nucleus and of the isospin variables of the nucleus. So the isospin, to remind you, I will discuss isospin in detail tomorrow, but just to remind you, so the convention is that you have isospin 1/2, the T is 1/2 for the nucleon, okay. And so you have two charge states, and the convention which is usually followed in nuclear physics is dz, so the projection on the z-axis of isospin plus or minus 1/2. So this is a neutron, and this is a proton. Okay, and so the idea is, instead of dealing separately with neutrons and protons, you say we deal with nucleons, and we will distinguish the two charge states of the nucleon by an isospin quantum number, and the isospin up corresponds to the neutron and the isospin down to a proton. Okay, the convention, this is the convention in nuclear physics actually. The particle physicists usually take the opposite convention. It doesn't matter as long as you stick to a consistent convention. Okay, you see here also that in principle you have a three-body interaction. You may have a three-body interaction because your nucleons are composite particles. Okay, and it can go on here. Okay. And so now the idea of the mean field, or the independent, which is the basis of the independent particle shell model, is to say, well, I will have introduced here sort of a potential which is felt by one nucleon, right, nucleon K, and you can think of this as the interaction that it has with all the surrounding nucleons. Okay, and this is just added and subtracted. This is the mean field, and this is the residual interaction. Okay, and in the independent particle assumption, what do? You just say, well, let's in first approximation forget about the residual interaction, which is of course a gross approximation. Right? And let's take an independent particle. This was called by Rick IPM, I think, independent particle model. Right? So this is the independent particle Hamiltonian, which is a superposition of one body operators. So that this one should very well understand, even if you don't have three body interactions, but one body plus two body, this is a very hard problem to solve once that A is a reasonably large number of nucleons. Whereas if you have this problem where you have only one body terms, this is, I wouldn't say trivial, but it's very manageable. And so the reason is because you have here one A-body problem, and you have reduced it with this approximation, you have reduced it to A one-body problems. And so you can solve the one-body problem separately and then put everything together. And so, yes?
May I ask a question? What is the meaning of dots in Hamiltonian?
Oh, so this,
four-body?
yes, this would be four-body because there is no reason that the series ends actually. There is no fundamental reason that there is no four-body interaction. So it can go on. One hopes that the effect will get smaller and smaller. Here, same thing, well, here already I dropped the three-body term. And actually in the lectures that I will give, I will always talk about just two-body interactions. But for instance, the algebraic techniques that I mentioned and what I will mention tomorrow, in principle they can also deal with three-body interactions. So there's no principle problem. Okay. So why is this easy, or let's say manageable? So you have now a Schrödinger equation for one particle, right? So you have this potential V1, this mean field potential which was introduced with actually one coordinate. Then you have a Schrödinger equation for one particle. And this is always solvable. I mean, in most cases you have a numerical solution, but it is manageable. Okay? And then if you have it for, so what you see here is states alpha. I will come later. So these are the quantum numbers that characterize. I'm assuming here that you're always dealing with discrete states, so this would be the discrete energy spectrum characterized by a set of quantum numbers which I will specify or detail in a moment. Okay? And this is a solution, these are the wave functions of one particle, so this is a one particle basis, and now the solution for many particles, at least the mathematical, also the mathematical solution, is just a product wave function, right? So this is acting on one single nucleon, this is acting on A nucleons, okay? So with the A coordinates of the A nucleons, and it is just a product of the single particle wave functions in a set of quantum mechanical states. Okay, so the way you should think about this is in the picture, so we have a potential. I will take here a harmonic oscillator, so this will be my V1, I assume. Right. So I have some levels in this potential, which I label by alpha 1 and so on. And so here I choose arbitrarily any combination of those will be okay, right? And I form the product. This is a mathematical solution. It's not the correct solution. This is one. It's not the correct solution because, of course, we have nucleons, we have fermions, so we have to impose antisymmetry. And the antisymmetry is done by constructing a Slater determinant, so the famous Slater determinant, right? And I will follow the convention always, because symmetry or antisymmetry or non-antisymmetric wave functions are essential to what I will discuss here. If I have a non-antisymmetric wave function, so just a product here, this in general is non-antisymmetric, I will use the symbol. This is fine. And so if it is an antisymmetric wave function, I will use the symbol psi. It's psi. Okay. So now you see, if look at the structure here, so you have the A particles, psi1, psi A, okay, and these are the different columns, and then the different rows are the label associated with a certain quantum state alpha 1, the label associated with a certain quantum state alpha 2, and so on. And of course, if now two particles are sitting in the same quantum mechanical state, so if alpha 1 is alpha equal to alpha 2, then you have a determinant with two proportional rows, and then it vanishes. Okay, so this ensures that you have a wave function which satisfies the Pauli principle. Okay, and of course, well, this is an example, and yeah, well, the energy of such a state, I am written it here. So just the sum of these single particle energies. No, it's not limited. It's just energies. Okay, so this is the eigenvalue of the many body states. This works for the non-antisymmetric wave function. It's the same eigenvalue for the antisymmetrized wave function. Oh, this one comment. So I have a set of slides, and the slides always summarize what I will say. Okay. There is also available on the Talent webpage a set of my notes. These are written notes, and there all the details can be seen. And so some of the derivations I don't have on the slide, I will go and do them here on the whiteboard, especially the tricky ones. So the difficult ones I will go slow and try to explain how it goes. And these, I mean, I don't have the derivations on slides, but they can be found on the web page. Okay, so what is the interpretation of this guy now? So we now have the rule that we shouldn't put two particles in the same quantum state, so we have to put particles here. Because these levels can be degenerate. That was already explained by Rick. And if there are degeneracies associated, for instance, with magnetic substates, that means several particles at the same energy, but they should not occupy the same quantum mechanical state. So if you look at the complete list of the labels associated, the complete list, I will specify it later, but it will be the radial quantum number, it will be the orbital angular momentum, and the projection of the orbital angular momentum, the spin, and the isospin. If you look at all the quantum numbers, then no two particles should be sitting in the same quantum mechanical state. So this is not allowed by the Pauli principle. And this is precisely obeyed by this later determinant. And this is a sort of a bit of a clumsy way of antisymmetrizing states. And so one of the goals of second quantization is that you do this in a sort of more compact fashion. So this I will explain tomorrow. And this is by means of relation and relation operators. I introduced here is one body potential, so the mean field potential, and without saying how do you choose it, where does it come from, and so there is a procedure to find the best possible mean field potential, and this is called active fog. And this is the idea in one equation. How does it go? So you want to minimize, this is a minimization, forget about this, this is just normalization, right? So you can assume that you have normalized wave functions and this is one. So, okay. But you should always work, if this works, if this can be forgotten if you work with normalized wave functions. Okay. So the delta here, what does it mean? It's a variation of a function. And so you can show that the Schrödinger equation that I showed in the beginning, completely in the beginning, this one. If I take this Hamiltonian and I do this variational principle, right, so my Hamiltonian is fixed, but I will now vary the kind, look at all possible wave functions, and I will minimize this with respect. Then this minimization problem is equivalent to the original Schrödinger equation. So that is nice. Right? This one can show. And so now what the Artin-Fock approximation is, well, to say, well, we do not take here a general wave function, we only take wave functions that are Slater determinants. Okay. So instead of doing a complete variation of all possible wave functions, we do a variation of wave functions of this type, right, where we have here the single particle basis that comes out of the potential T1. And then we have a sort of an iterative procedure. How do we do it? We choose a certain potential, mean field potential. We solve it. This gives our basis. Okay. And then we can calculate this this integral here. And I should mention, stress the fact that here we take the full Hamiltonian, not the independent particle Hamiltonian, the full one. Okay. You calculate this, then you do a variation of this potential. We change a little bit the wave function, the single particle basis. You look and you see whether you have minimized the energies or not. Okay. So this is Artin-Fock procedure. And so it is trying to minimize the energy of the system, assuming that you have a Slater determinant. What is important is that these are solutions. These are the solutions of a single particle problem, okay, of an independent particle problem. So these have not. These are not the solutions of the full Hamiltonian. Okay. But the minimization, in the minimization here, you can, without any problem, choose the full Hamiltonian. Okay, this is just something about Artin-Fock approximation.
So,
yeah.
Before we go on, I guess I'm still a little confused on how choosing to represent your wave function in Slater determinants is an approximation. Like, what information are you losing by representing it in this way?
Because it's only one single state. So normally what you should do, if I go back, you should of course, let's forget about three body, okay? And let's say when we just have two body here, you should put in this residual interaction. Okay, this should be there. Okay. If you put that in, and then you construct states, all possible states here, so you put your particles in the way you have already done with Rick, so basically, put my pen. basically the ground state will be filling all the particles up to a certain level, so that will be one state. But then you will be other states where you put one particle here. These are all Slater determinants. It's all different Slater determinants. You have, in fact, you have an infinite series if you don't make some kind of an approximation where you said, well, I will cut off the levels at some energy, for instance. Now, so you have a series of Slater determinants, and this will be a basis state. This will be your basis, and in this basis, this interaction, this residual interaction, is not diagonal. So you have to construct your matrix in your Slater determinant basis and diagonalize it. So that is a much more complicated problem than the Hartree-Fock, which, okay, said I will take a basis which is an eigenstate of this Hamiltonian and then calculate the matrix element of the full Hamiltonian in that state. So this is an approximation. That clear?
The difference is still really subtle to me, because it seems like we're just building our basis out of Slater determinants, but as long as this basis is complete and orthonormal, we should be able to get the full solution.
Yes, that is true.
So
but
how's
that's
that?
very difficult.
Okay.
Because then this basis is infinite, and even as I will show, I think tomorrow or something, Rick already showed, if you now construct, even if you do a modest truncation, I mean that you say, well, let's consider a few the valence levels here and put particles there, your basis becomes huge.
Right.
And so you have an enormous diagonalization from in front of.
But to me, that seems like the approximation is drawing a line somewhere. Not, as long as you're using the full infinite basis, it should not be an approximation, right?
That is right. But Hartree-Fock is not at all that. Hartree-Fock is no diagonalization. It's just a Slater determinant, and you minimize the full Hamiltonian in that Slater determinant. If you do a correlated calculation, so if you do construct all your Slater determinants and then do the diagonalization, your ground state will not be a single Slater determinant. It will be a superposition of them. Right? And so often what is used is the term correlated wave function. Okay? That refers to the fact that you have a superposition of different Slater determinants. We will not be doing Hartree-Fock, or at least I will not be doing Hartree-Fock, but I will look at the problem of constructing some kind of Slater basis and diagonalizing it and actually seeing whether there are some simple solutions. Okay. This is something, this is actually the title of a chapter of Lawson's book, and I sort of like this. He calls it Pullman's Hartree-Fock. Okay. So what is the potential that you would get from sorry, Marek. So if you do this, what would be the best, or let's say realistic mean field that you would obtain? Would be looking something like this. It has a flat bottom. And it goes like that. Okay. This was already discussed by Rick. And unfortunately, I mean this. So here you would get eventually P1. It's very symmetric, at least here. And this, of course, this can be solved. The learning equation associated to this potential can be solved for a particle. And we can construct later determinants. The problem with this is it's not an analytic potential, right? So you cannot solve it analytically. And one potential you can solve analytically is a harmonic oscillator potential, which goes something like that. So this is like proportional to r squared. Okay. And actually there are two potentials, well, two simple potentials which can be solved analytically in 3 dimensions, or in n dimensions actually. One is the harmonic oscillator and the second one is the Coulomb. And well, harmonic oscillator is better suited for nuclear structure. So you take a harmonic oscillator. And so where is the poor man? The poor man is, of course, you do not take a mean field potential that comes out of your Fock procedure. You take something which is an approximation. Okay, let me discuss a little bit because I would like to make some points about adding these guys, but let me first assume that I have a pure harmonic oscillator. This you probably know. This is harmonic oscillator, and there is nothing else to it. Okay, and what you probably know is that the eigenfunctions of this guy can be written as they depend on spherical harmonics. That. So they have a radial wave function, which depends on the oscillator. The radial quantum number, so which is related to the number of nodes, this depends on R. And then we have spherical harmonics. Okay, so this would be a solution if you, at the moment I don't want to discuss spin, right? So this would be the solution for the spinless particle. And so out comes the radial quantum number and the orbital angular momentum. Right? So this is the angular momentum which is associated with classically, so the angular momentum vector is r plus p. Okay, so this is the quantum mechanical analog, and then NL is the projection of the angular momentum, the orbital angular momentum on the z-axis. So this is the solution in terms of spherical coordinates. I hope everybody knows what spherical coordinates are. So you have x, y, and z. You have a point here. This is r, the projection. So this is theta, the angle between the r vector and the z-axis, and then this is phi. Okay, so this is the definition of spherical coordinates. Of course, you can also solve this harmonic oscillator in Cartesian coordinates. This we will do in one of the exercises. But it's more convenient to do it with spherical coordinates because of the spherical symmetry and the definition of the orbital angular momentum. So these wave functions are characterized by good orbital angular momentum immediately. Okay. Now, we have to put in spin. Okay. So how do we do that? So let me use this notation that we often just Now, I would like to put you multiply it. The spin is 1/2, but then it's characterized by the projection of the spin on the z-axis. This is, I will put label K in general, and so this is then the spin now which is associated with the particle K. Okay? And so this will be a solution of this harmonic oscillator potential, right? It's independent of the spin, right? So the spin doesn't come in. But if your particle is spin, this would be the proper eigenstate of that Hamiltonian. Okay? Now, this is inconvenient to use. Why? Because it defines the orbital angular momentum, its projection. It defines the spin and its projection, but it doesn't define the total angular momentum. And we will see in a moment, it's nice to have the total angular momentum. So if you look at the properties of the operator L squared acting on this wave function, it will give Ln plus 1 times this wave function. Similarly, if I act, well, I should put here, if I put the units eta omega squared, right? Act on Lz in this state, what is the eigenvalue? It's just L with R. Same thing for S squared. It will be G4 8R squared. And finally, Sz. This is possible. This is the basis of your Hamiltonian for a particle with spin, but it's much more convenient to use a basis of this type. This, which is 1/2 J and J. And how do you define it? It's just a superposition of Clebsch-Gorlin coefficients L and L, 1/2 ms to J and J. The summation is over the projection of the orbital moment and the spin, and here you have your original. So this is just a unitary transformation from one basis to another basis, and these are the famous Clebsch-Gorlin coefficients. And so they are here used for the case of coupling orbital angular momentum with spin 1/2, but they can be used for any angular momentum, system J1, with angular momentum of a system J2 to a total angular momentum J. Okay. And the nice thing of this is that now you have, let me erase this. If I now put in here my wave functions, this, L squared is still defined, so it's L plus 1 h bar squared. In the M scheme. Then you might say, well, what is the advantage? Well, let's suppose now let's put in isospin. So let's put in isospin. Okay. So now I will consider a wave function which is characterized not only by the coupling. Well, I should put also isospin there. And let me put it for J as J1 equals 2. I couple this to J, total angular momentum, its projection mj, and I do the same thing for isospin. Okay, I have two particles, they have isospin 1/2. So the t can be 0 or 1. Okay, the coupling of two 1/2. Let's now do the same argument. I apply my permutation operator. This guy, so I will interchange all the coordinates associated with particle 1 with all the coordinates of particle 2. So now maybe I should just write explicitly the same thing we have to do isospin. It's 1/2 for one particle projection in T, 1/2 for the other particle in T, and then of total isospin. Okay, and so this in terms of the on the couplers. I should put here now explicitly this is okay, so this is the equivalent, but now written of this kind of expansion, but now it is done, the coupling in spin, in angular momentum, I should say, angular momentum, and in isospin. Then you go to the same arguments, you do these switches, you use the symmetry properties of the Clebsch-Cohen coefficients, and so what you will find is that you have, this is a J plus T, so the rule is, if we are dealing with fermions, then it is J plus T must be all. I want to construct a wave function which is completely antisymmetric, so I find the rule J plus T must be all. Of course, if T equals 1, if we have two identical nucleons, that means that J must be even. Right? So, of course, I find back the result that I derived here, but now I can say if I couple two nucleons, whatever they are, okay, two nucleons, the sequence of JTs that are in the same orbit, the sequence of JTs that are allowed is 0, 1, plus 1, 0, plus 2, 1, plus and so on. And the maximum, of course, the maximum angular momentum is 2J. Right? And then if I have this, of course, this is an odd angular momentum, then the T is easy. Okay. So you see that in the beginning this might say, well, I just find the same result as I did in the M scheme, but then it's powerful because we can put in a simple way a consideration of isospin. So now we know the rule. What are the spins and the isospins we can obtain for two nucleons? Two nucleons in general, neutron functions. Okay, so this yes, this I think is a good time to have also this is a summary. This is a summary, it's essentially what it was here. You can write it in a little bit different, so this is just picking out the positive checks. Okay, I would like, I think I will have a break here because what I will do after the coffee break is to do this problem for 3 particles. And this is, you will be confused and amazed, and this is a difficult problem, but don't worry about it, there will be exercises on it. Well, maybe you should worry about it then. But hopefully these exercises, they will sort of give you a better understanding of this has to do with this famous or infamous coefficients of fractions. So back in half an hour. Yes.
Can I just ask one question? We have 1 minute.
Yes, yes.
You referred to the one-body potential.
Yeah.
You also referred to the idea of mean field.
Yeah.
What do you mean differently by the two?
Yeah. The kinetic energy, of course, is it's included in the one-body term, right, of the independent particle.
And by mean field?
I'm not sure. The one-body potentials refers to the potential. Okay? Mean field, I would say it includes all one-body, including the kinetic. But it's a semantic.
I ask because a lot of people are confused.
But in the one-body term, of course, includes the kinetic energy. And it's very important because in many ways the two contributions are cancelling each other. Okay, are there any other questions? If not, then because this is something which is often talked about with shell model. Nowadays, shell model calculations, they always use Jacobian scheme, and I guess now all the codes are actually written in the M scheme. So they're not using these complicated bases that I will discuss for 3 particles, but they're using an uncoupled basis. Right? Numerically, this is much easier. Right? Nevertheless, historically, I mean, LS coupling was important at the beginning of nuclear physics, because it turns out that LS coupling is the approximation that you make in atomic physics. That is the correct coupling.
Can I just ask you,
Yes.
do we call it in nuclear physics Russell-Saunders coupling, or it's just for the atomic physics?
it's also known as Russell-Saunders couple. It's, for me, it's synonymous.
Just like out of the norm.
But it's, of course, that is a term that came from atomic physics. And historically, I mean, people were thinking about telescoping, at least until the end of the 40s, because there was no need for introducing, or there was no argument for introducing J.J. Copy. So let me try to explain to you what is the difference between the two schemes. And again, it is here, it consists of a unitary transformation between two bases. Right? So there is no, if you do a shell model calculation, you can do it in principle in J.J. copying scheme, you can also do it in LS copying scheme. It will give the same results, or it should give the same results. Right? But it might be more convenient to use one coupling scheme with respect to another, because in one coupling scheme your Hamiltonian might be close to diagonal, whereas in another coupling scheme it might be a very large off-diagonal matrix elements, and it mixes the basis states so that it becomes more difficult to do the interpretation. Okay, so now let me try, and I will do this with two particles, and I will try to explain with two particles what is the difference between J.J. coupling and LS coupling. So we saw a three-nucleon state which is just coupled in angular momentum, and so let me immediately And so yesterday there was already a remark. People asked me about this because you can in principle construct three-nucleon state not in the M scheme, but just by coupling them to an intermediate, two particles coupled to an intermediate angular momentum, J prime, and then the third particle, which you then couple to Kender to total angular momentum J and J. Okay? And this written. So that's what
You use the same J's, like the small one?
yes. Let me immediately do it with same J's. Okay.
Do you think we can remove the screen temporarily, because I can feel like that you need for the three particles?
Yes, maybe that's good.
What?
I knew how to do it.
Is it not a mechanical one?
No, this is ultimately there's so many.
No. He's not going to show
Yeah, maybe.
but I can't.
No. I think it will be difficult because then the projector also.
I
yeah, the complicated.
Yes. Okay. Okay. So this is just a coupled wave function. Okay. What we have to do now is to antisymmetrize it. Okay. So you have an operator. You take all the permutations of three objects. This you can write the notation that I introduced before. So this doesn't do anything. This interchanges particle 1 with particle 2. So then we have minus p. Let me do the same in the notes. 1, 3. 2, 3. Okay. These are 6 permutations. And if you work it out, these are exactly the permutations of 3 objects. Okay. So now what you have to do is apply this permutation operator on that state. Right, and I will immediately, this wave function will be antisymmetric. How did I get it? I had it from, it's a 3-particle wave function, and I obtained it by taking an intermediate angular momentum J prime here, and then coupling to angular momentum, total angular momentum J. Actually, the thing, well, I will also do permutation. This now depends on psi 1, psi 2, psi 3. 3 particles. Here I associate the particle at a certain position. So in this case it's completely antisymmetrized because this has arisen from the application. I'm not doing the normalization. I just apply my antisymmetry operator on this way. I'm going to destroy something. Is it still on?
No. Well, it restarted.
Maybe we don't need it anymore.
Well, there will be 1 million viewers.
1 billion.
Because this will be put on the internet. And it will like,
It'll go viral.
Psi 2 billion, right? So
It's just a question of advertising.
I'm not so sure.
You don't have to tell them that it's physics. It's just, they have to click on it and then it counts.
What do you mean by putting J prime in the brackets? Like it's...
Oh, yes.
This is the intermediate, yeah?
That is, yes, that's an important point. Yeah. So it means I have obtained, I will now write it here explicitly, I have obtained this state by constructing a coupled state like this with intermediate J prime and then applying the antisymmetry operator. That's all I say. I have not yet discussed what this label. This is some kind of a label. Yes.
Because I use an intermediate coupling, do I just do this because the formalism with the Clebsch-Gordan coefficients is only suitable for 2 particles coupling, or two angular momentum spins coupling to each other, or is it there a possibility to have a formalism that is capable of coupling 3 particles to each other?
I wouldn't know how to couple at once.
Okay, so yeah.
there might be some fancy Clebsch-Gordon coefficients.
Yeah, maybe I don't know.
Yeah.
Maybe some guy already invented it. I don't know. Or,
Ah,
Yeah. Okay, do I need to write this? Right, so this is this guy, fine. Maybe I should. J prime. This is. So now it becomes a technical problem. I have to apply all these permutations in that wave function. Okay. This is the time.
So could you come up? The Slater determinant was kind of just a nice compact notation.
Yes.
Is there maybe some kind of generalization to a three-dimensional tensor you could just?
But you see, the Slater determinant, when I put alphas, okay? I had my wave functions like this, alpha 1 of psi, alpha L of psi k, okay? And I was a bit cheating because I didn't tell you exactly what this alpha L was. Well, I should just put alpha, okay? And this alpha is the complete set of quantum numbers. So it's n, L, if I do it with spin, so spin S, J, Mj. Okay, so I have uncoupled wave functions. I would be using a basis like this. I have no total angular momentum. So the Slater determinant is not coupled in angular momentum. I can easily, as you saw, it's antisymmetric, and that's a trivial thing to obtain. It's just taking the determinant. Unfortunately, it's not coupled in angular momentum. This is the opposite. Here it's coupled in angular momentum, but it's not antisymmetric. So that is the problem.
Okay.
Get both properties at once.
Sir,
Yes.
how do you construct this parity operator?
This P operator. Well, this you have to work out for yourself. But you see, you know, this is all the permutations on three objects, right? If you have an odd permutation, so only one permutation, then the wave function should pick up a minus sign. If you have an even permutation, then the wave function stays itself, right? You do two permutations, you should obtain the same wave function. Okay? And so now, this for instance, you don't do anything, you don't permute. Here you permute 1 and 2. Okay, so this is an odd permutation, so you pick up a minus. But here you permute 2, 3, 1 with this, so it's odd. This is a double permutation, P2, 3, P1, 3, so minus, it's even. So this is the fourth, this is the fifth, and this is the sixth. They're all different. We have 3 plus signs and 3 minus signs. This is some way of writing the permutation. It's convenient for the derivation of the below. Okay, so let's look at the action of this guy, that one. So, I say here proportional, right? So I haven't normalized this. I just would like to construct a wave function which is antisymmetric. I apply this antisymmetric operator. Okay, so you get the same thing. Minus P12. just interchange particle 1 and particle 2. Okay. Now this we know, because this is just the interchange of two particles in the same orbit coupled to angular momentum j prime. So we can get back to this one if we put in a phase. Okay. This is just like two particles, and I don't want to rewrite every time the whole thing, so I just did the permutation, and I know that if I do this on a two particle state with a total angular momentum j prime, I pick up minus times minus 1 to the power j prime. So this gives plus minus j. Okay? This is quite normal, because now you see if the j prime is odd, the thing will disappear. That's quite normal, because we know the first two particles should be coupled here to an even angular momentum. That's the only way the state can survive. Okay, so now this becomes difficult to do. Okay, so minus. So you will see how the permutation will work. I will now show explicitly. So I do P23 with this one. So I exchange 2 and 3. Okay. And then I do minus minus P23 P13. It's a plus sign. So the only thing I have to do, I have already here the wave function P23. I have to interchange this. Okay. Interchange P.
Can I just ask a question? So
Yes.
you're just going with this A1, 2, 3 operator over the wave
Yes.
function,
Yes.
but so you have this phase change which is minus 1 to the j prime because the particles are coupled to j prime,
Yes.
but there is also some minus from the operator, which means j to the minus plus 1.
Oh.
You understand what I said? I mean, yeah.
Yes, but this must be the result, right? Because here you have the result that if the j prime is even, the thing exists, right? If the j prime is odd, this will cancel that. So that is precisely what you want.
Okay, but in general, if you couple two particles to speed j, then you want to permutate their wave function,
Yeah.
the phase factor that comes is minus 1 to the power of the j that you couple them to.
No, the phase factor was minus to the power j. Okay.
Yeah,
The action of P.
yeah. There is also one minus in front of the operator.
But there is a
So
minus in front, so it
Plus.
becomes plus. Okay.
Aha. Okay.
Yeah, this, I will try to do this correctly, but this is a, do this. Okay, what happens here, you see the same system again, the same feature again. So here 1, 3, here 3, 1, and we know we can do that with interchange again. Right? 3. And we have to introduce the okay. Last two, just to make you happy to see that we have all the permutations on these objects. 6 different permutations. So here it's 1 with 3. 3. 2 doesn't do anything, so I leave it. And here it's 1. Okay, and then the last one is minus minus, so it's plus. Yes, I must have made a mistake, I think.
That one's minus.
Minus, yes. This is plus. No face. Face is one. And so here it's 2 with 3. These two. Same argument again, I can switch 2 and 3 because this is a 2 particle state. And if I have everything correct, we should do minus. And then you see I can take this and this together. This and this together, I have 3 terms. But I'm still not fortunately. Now it gets complicated. Because this is fine, so I have the particles in a specific order, which I would like for all the states to have 1, 2, 3. 1. Here I have 1, 3, 2, so I have to switch particle 2 with particle 3. This can be done. This can be done with, remember the coupling, which I erased, with the coupling of 4 angular momenta. So we had a coupling of L1 to J1, L2 to J2, and then an alternative coupling of the L's. This is a similar problem. Okay? This is a problem where you have angular momentum associated with particle 1 and 3. And I want to change particle 2 and 3. This can be done. So that's now an overall phase for the first term. The first term is trivial. It is trivial. And so now the second term, I have to switch the second and the third particle. So this is a linear combination, which is a minus 1 and not. Now I have them in the correct order, being 1, 2, okay, and the last, we can do a similar term. Oh, I forgot, I should because they all have this factor.
In
1
this 6J,
plus.
in
Yes,
this
I
6J,
will explain.
but is J small big, or the second one is big? Okay.
This one, is it clear now? Right, so this is a 6J symbol, it's something similar as this one is a 9J, this is the recoupling of 3 angular momenta. Here This is the recoupling of three angular momenta. This is four angular momenta. This is the recoupling of three angular momenta. So again, it's a standard expression in terms of, this is known as a summation. And actually, this we will be using this afternoon. And so this is part of Mathematica routine, where you can calculate 6J samples. Okay, the last term here is without. And again the same. This is, you see here, this is a smart result, this is a nice result, because you see you have a summation over here intermediate couplings of particle 1 and 2. This is, in principle, this J double prime, it can be odd or even, but you see one term comes with -1 and the other one with +1. And so only the even angular momenta J double prime will survive. And so you will see now, this is automatically a two-particle state with even J double prime. So this is automatically a two-particle state which is antisymmetric. And so you can now write everything in a very compact way. I have antisymmetric wave function. I'm going to write this, or this I did already there. Jm. I have a summation over J double prime, and then I have a coefficient, right, which I will explain in a moment. Which does not depend on Mj. And then here, this wave function, as I said, it's only even J, so automatically I have an antisymmetric state for the two particles. So I write J square equal to J double, and this depends on particle 1